or a cylinder one. What we have is a conical container. Okay. So since it's a cone, it's not going to be producing a height that can be graphed like this. Okay. Since it's a cone, it will be filling in fast, and then as it goes up, it's going to fill in slowly, which means now that the graph that we will be getting is something like this. That's our graph. So it's a curve. Now, so what we have here is as this fill in, obviously we have several components that changes. The depth or the height of the water, H, okay, and some given information. The height of the container from top to bottom is going to be 12 centimeters. And the radius of the top, okay, of the container, the radius is 4 centimeters. Now, if the water is filling in, if the volume or the flow of water is filling in at a rate of, let's say, 10 centimeters, cubic centimeters per second, letter A, the question is find how fast, find the rate of change wait, wait. Find the rate of increase in, not volume, in depth. Okay. Since we place height, let's use height. Okay, so, so that's our job. Find the rate of increase in height of water in the cup when the height is at 1 centimeter and 6 centimeters. Okay, so this is now our problem. We have now again a connected rate of change wherein we need to relate two, what's this, two components. What components are we comparing this time? Anyone? What components are we comparing here in this problem?
Is it dH over dt?
dH dt or the height? Yes, okay. So according to this, we are looking for how fast is the height changing, how fast is the height changing inside the cup? This one, okay? So you are correct. We need to find dH dt, okay? So that's one. So we need to find the height. But what else? What is this?
Uh, Rate of water flowing.
Rate of water
Humidity.
falling. So this is now cubic
Humidity.
centimeter. Yes, that's volume. So this is now going to be dV per dt. So we are actually trying to relate volume with the height. Okay? So since we are relating volume with the height, what do we need to compare them? We need to compare, or we need to find what? We need to find dV dH, correct? We need to find dV per dH because we need to multiply it with dH per dt. The dH will cancel and what will be left will be dV dt, correct?
Yes.
dV. We have this dV dt. This is what we are looking for, dH dt. But we need to find dV dH, meaning volume in terms of H. So we start with that. We need to find volume. Okay, so volume of what? So what function are we going to use?
Volume of a cone.
Volume of a cone. Okay, can you give me the volume of a cone? No, suddenly quiet. What's the volume of a cone?
I forgot to share it. Is it?
Forgot.
Forgot.
One per
You must
three,
be.
one,
Uh-huh.
oh, 1/3 times the area of the base times the height.
Correct. Wow, Charson. Area of the base times the height. So you still remember that. Okay, so give it to me in detail then. So 1/3 because it's pointed, correct? Whenever you see a pointed figure, be it a cone or a pyramid, it's always 1/3, okay, of the original one. Original is the cylinder, so 1/3 of the cylinder. So volume is equal to 1/3 area of the base. That's a circle,
Phi r squared.
pi r squared times height,
Height.
correct? Okay.
Yes.
So there, height of the cone, huh? Height of cone, not height of water. Okay, so I place there height of C, HC, height of cone. Uh-huh. So it gives us now a problem. It gives us a problem because this is in terms of radius. Radius, and it's not H, right? We need dV dH. Oh, wait. We need the volume of water, so no need for the C over here. So H, yes, okay, H. The problem is the R is unknown. This R, from here to here, that R is unknown. We cannot get the volume of this water if we do not know R. Furthermore, we also don't know H, right? We don't know this. So there are two unknowns in this formula. Can we differentiate it? No, because we need in terms of H, one variable aja. So what do we do? You get what I'm trying to say here?
Yes.
We need to
Yes.
to get the derivative of the volume in terms of H. H is there. Okay, no problem. The problem is R. We do not need R. So how do we need, what will we do to remove R? Suggestions?
Pythagoras. Not sure.
Pythagoras?
Using ratio
Why? What's our purpose to use ratio?
to get the ratio.
Yes, I know. We use ratio to get a ratio, right? Okay, but what's the purpose? Why do we need to use ratio?
To know how much is the R in H.
Okay, good. So we need now to express R or the radius in terms of H, so that we have just a single variable here in this equation. Okay, so R in terms of H, and to do that, we now need to look at the side view of this container. Okay, so the side view of this container is basically an isosceles triangle wherein we have two information. The half distance from the middle going to here is actually 4, while the height is going to be 12, correct? From here to here, that's going to be 12. If we compare it to the water, since it follows the shape of the container, these are two similar triangles. This small triangle formed over here is a smaller projection of the big triangle over there. So they are similar, okay? Which means now that this is the R that we are looking for, and from this distance going down here, that is now the H, okay? So we have, even if we just look at half of it, these are now two right triangles. Big triangle is small triangle, which means we can now make our proportion, ratio and proportion. I can relate these two together. R per H, this must be equal to what? R per H is equal to
4 per 12.
4 per 12.
4 per 12, correct, okay? So, yeah, please guys, these are very basic operations that I expect you to have mastered several years ago, okay? So ratio and proportion, everything comes into play now. We use everything that we have learned before, okay? So here, we have here R per H is now equal to 4 per 12. We can now solve for R in terms of H, meaning that is now going to be 12R is equal to 4 times, correct, right? 4H, and then what? Divided by 12. So that is now what? R is equal to H per 3, correct? Am I
Yes.
correct?
Wait.
Yes.
Yes.
4
Yeah,
per
yeah.
12. 4H, right? Okay, so which means we can now use this to substitute in place of R squared. And our resulting function now for volume, so volume now is equal to, what's that? 1/3 pi. We have R, it becomes now H per 3 squared times H. Simplify further. Simplify further, this one now becomes
1 over
H squared
27.
over 9. 9 times 3 is 27. So 1 per 27 pi.
H raised to 3.
Okay, so there we have it. So we have now a function of volume in terms of height. height aja, no radius. Okay, so this is now what we're going to use to find this. Okay, so that's a volume. This is now height. So we need to get what?
The derivative.
dh. Okay, if we get the derivative in terms of h, we end up with dv dh. dv dh is what?
Is it 1/9? Then
1/9
pi h raised to 2.
pi h raised to 2. Done. Okay, we're done, right?
Then we input the numbers there.
We need now to fill in this information to be able to answer the question. Okay, so dv dt is what?
10
dv dt is
centimeters cubed per second.
10. Okay, is equal to dv dh is
1 over 27.
pi h squared over 9 kali
Times
dh over dt. Okay, cross or dividing both sides with this, we will now get what? dh per dt is equal to
In decimals, teacher.
just leave it as pi.
So it would be 90 over pi.
90 over
90 over pi h squared.
pi h squared. Okay, done. 90 over pi h squared. This is now our function for the speed or the rate of the height, how fast it is now moving up or increasing. We need to evaluate this one two ways. When x is equal to 1 and when x is equal to 6. Okay, when x is equal to 1, what do we get?
Is it x or h, teacher?
Oh yeah, sorry. I got used to x. We have here h. Okay, when h is equal to
We'll
1?
get 28.65.
28.6. When h is equal to 1, that is now 90 per
Right.
90 per pi,
Yeah,
correct? Which is now equal to
28.65
0.65 units,
centimeters per second.
centimeter per second. Okay, that's how fast it is moving at h equal to 1. How about when h equal to 6? It will give us 90
0.
per pi
pi times
h.
36.
20, what's this?
6 or 36.
6 squared is 36. Okay, how many?
0.8 or 0.7.
0.8.
Yeah,
No, 79. Let's just use 79.
you got 795.
795
Yeah,
centimeters per second. Okay, so which confirms at lower levels, at let's say height 1 centimeter, since it is still very small, it goes up very fast, 28.65. But at 6 centimeters, since the volume now or here, it's wider, the mouth is wider, it's moving now, it's moving up with, which is very slowly, 0.08 centimeters per second. You get the idea?
yes, teacher.
Okay. So
Sure, I want to
there.
ask you, teacher.
Yes.
Why do we have to change the volume in the first place again? The volume
Why do we
equation.
need to change the volume function to, okay. dV dH means all of this on the right side must be in terms of h. You get the idea?
Okay. Yeah.
Right? Because right now we have two variables, r and h. It's like saying, it's like getting your dy dx. Okay, you're looking for dy dx, but then you have here x squared plus z. You cannot use this in dx because you have z, another variable.
Oh, okay, teacher. Yeah.
Clear? Okay. So here, all of the, on the right side, to get the derivative, everything must be in terms of a single variable. Okay. So, other questions?
None.
None. Okay, can I erase? We still have around 10 minutes, right?
Yes.
Yes. Okay. Can I erase this one?
Yeah, sure, teacher.
Yes, teacher.
Yes, okay. Next. Next is seen, always seen at the ferry terminal. Here is now the sea. Here is now the pier. And whenever a ferry is going to arrive, okay, let's draw a ferry something. Let's say we draw a boat over here. Okay, you see people throwing a rope, okay, and then they pull the boat in, correct? Yes?
Yes,
They
teacher.
pull the boat in so that it will not collide with the pier very strongly, okay? So the question here is, when this man pulls the boat, will the boat move up like this?
No.
No, what will happen? The boat is just
It
going
will,
to
yeah, move horizontally forward.
boats move horizontally, okay? Which means now that you will be seeing two movements here, okay? There are two movements. How fast, okay? How fast the rope is being pulled. So if that is now, let's say Z, okay? The man is pulling the rope very fast or at a certain speed. Obviously, the ship or the boat is also going to be moving horizontally at a certain speed. The faster the rope is pulled, the faster the boat is going to move towards the pier, right?
Yes.
So this one now, if I'm going to label that as X, then we have now a change in the Z. We also have a change in the X. Okay, so my question now here is, if this rope is now going to be pulled at a speed of 2 meters per second, 2 meters per second, and the pier, this, let's make it smaller so that it's easier to identify, okay? And the pier is, let's say, 3 meters high. 3 meters high. That's the height of the pier. Okay. How fast? How fast is the horizontal? Or what's the rate? It's okay. How fast is the horizontal movement of the boat at 4 meters away from the pier? So that means when we reach a certain distance, when we reach the certain distance 4 meters away from the pier, how fast now is the boat moving? Okay, what are the information that we need? We need what? What do we need?
Is it DZD? And
Okay, this one is dz dt. What else?
XD horizontal.
Okay, we need our horizontal movement, dx per dt, how fast that is now moving. This is the unknown. And we need to relate them together, right? We need what?
Yes.
Okay, so let's see. Dz dx. Yeah, we need dz dx, dz per dx, because when we multiply this together with dx per dt, we have that, right? The dx will cancel, and we will be ending up with dz per dt. Okay, you got the idea on how I came up with this formula?
Yes.
So how do we find that information that we need? We already have dz dt. This is what we are looking for. So the question is, how do we find dz dx? Come on.
Is it Pythagoras?
Yes, it's Pythagoras. So technically, this forms a triangle, a right triangle. As you pull further, pull it like this one will move farther forward, correct? So that's now 90 degrees. So we can solve for z, or if you do not want to use my triangle like this, you can use it like this, okay? But basically, let's just use, it doesn't matter anyway. This is actually a good diagram, okay? So this is now going to be what? Z equal to square root of
Squared plus 1 squared.
x squared plus 9.
3. Yeah, 9.
Yeah. So let's remove the square root by placing the exponent. Z is equal to x squared plus 9 raised to 1/2. Okay. So I just need to do what? I just need to find dz dx because this one is right.
Yes.
To find dz dx in terms of x. Okay. What will be our resulting function?
Half times.
Half times?
Wait.
Half times everything inside, right?
Yeah,
X
that is.
squared plus 9 raised to negative 1/2
Times 2x.
times 2x. Okay, times 2x, which means that's half. And then this is now 2.
So that would be
Simply x, right? Okay, let's just use that one. So dz dx, this one, it's annoying. So just remove that. So dz dx is equal to x times x squared plus 9 raised to negative 1/2. Okay, let's use that. So this is now going to be placed in this formula. We will now get dz dt, that's now 2 equal to x times x squared plus 9 raised to negative 1 half. And this is now going to be dx dt. Okay, next step, to find dx dt.
We divide both sides by x times x squared plus 9. Raised to the power of negative 1 half.
And then,
And then
yes, then
we insert 4.
what will be your dx dt?
Okay, wait. Is it 2 over? Wait.
Hmm?
Hmm. 2 times square root of x squared plus 9 over x.
That is now x per x squared plus 9 raised to 1 half times 2. So 2 like this divided by x,
Yeah,
correct?
yeah.
So that is now going to be 2x squared plus 9 raised to 1 half raised to 1 half divided by x. And this is now going to be evaluated where x is equal to how far?
4.
4. Okay, so how much?
I got 2.5. 5.
2.5 what?
2.5 exactly.
Yeah, 2.5 units
Oh, meters per second.
meter per second. Okay, done.